Hey there, rock stars. Let's get rocking. The purpose of the video is a couple-fold. I want to talk a little bit more in depth about the perpendicular bisector theorem, and also maybe give you a chance to see what I'm looking for in terms of the proof, because we didn't really get to talk at all in class about what the proof looks like. We just talked about the big ideas of the proof, but never actually got down to the steps of writing it. And that's something you are going to be held accountable for, something I'm expecting you guys to be able to do, which is to produce this proof on demand. So with perpendicular bisectors biconditional theorem, with biconditional really being an important word here, biconditional of course implying that this statement, this conditional statement, is true both in its original form, with the if point P equidistant to both A and B being the given information, and also in its converse form, assuming that the current conclusion, P is on the perpendicular bisector of segment AB, is our starting information. Pictorially, the perpendicular bisector theorem needs to reflect that. So if I'm looking at this biconditional theorem, both forward and backwards from its original theorem, we have to kind of track this information carefully. So here's what it's saying. If I pick this point P, just anywhere in space, if I have this line segment AB also on a plane, as long as I pick point P, so that P is always going to be equidistant to the endpoints of the segment. So if I pick it in such a way that this is true, then as a result, that point P will always appear on the perpendicular bisector of AB. So, being biconditional, it doesn't matter if I start by picking that point P so it's equidistant, or if I pick that point P that's already on the perpendicular bisector. It gives me the opposite conclusion. So if I just pick this point, if I say I have this perpendicular bisector L, pick a point P on it, like this guy, then automatically I know that point P is going to be equidistant to the endpoints of AB. Flip it around, if I pick a point P, as long as I pick it so that it's equidistant to B and to A, equidistant of course meaning equal distance, I know that P has to be then on the perpendicular bisector. Hence, biconditional. It's true no matter which part you actually start with, which is something we've toyed in with in the past, but never really went much in depth with it. So how do you prove this? Well, you prove it by actually showing us two cases of proof. One for the original statement, starting with point P being equidistant, in other words, going left to right, and then also to prove its converse, going backwards. So let's do that. Let's start with the original statement. If point P is equidistant from both A and B, then P is on the perpendicular bisector of segment AB. In other words, looking at the diagram, this is going to be kind of copying from what I had before. If I had this line segment, a perfectly straight line segment AB, and I pick this point P, I know in terms of starting information that it's going to be congruent to both A and B. I then have to show that this point P, along with all of the point P's, which would form a line, so if this is P1, I can pick another P on the line segment AB, called P2. I know the line that is formed between them, I have to show the line formed between them is 1, at a right angle, and 2, bisecting AB. In other words, cutting into congruent parts. Well, how do I do this? Well, you guys established well in class that it was still centered around proving triangles congruent. If I want to prove that AP2 is congruent to P2B, and I want to prove that these angles in the middle are right, it really amounts to proving that these triangles, AP1P2 and BP1P2, are indeed congruent. So that's what you're going to see. I'm first going to try to prove the triangle's congruent, and then from triangle congruency, show the parts I actually need. I just need more information in this diagram than I currently have, and the best way to get that information is to actually prove congruency. Excuse me. In fact, it almost kind of writes itself. I mean, if you're looking at this triangle, I don't know this angle is 90 yet, but because of the way I'm picking P2 to be on B1, B2, P2 to be on AB, I know that these are congruent. Well, all I need is one more side, and lo and behold, I have a reflexive side in the middle. So I'll prove the triangle is congruent by side, 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 and then work from there. Okay, so my first step. Whoa. Okay, so my first step, or step 1, will be to go about proving triangle AP2, P1 is congruent to triangle B, P2, P1. And I'll do that by using side-side-side congruence. So side, side, side. Okay, so side 1, I'll go ahead and use the reflexive one. I can claim that P1, P2 is congruent to P1, P2, and that's simply because of the reflexive property. Okay. For side 2, let's go to the outside ones, the diagonal ones. I know that AP1 is congruent to BP1. And that's because, what am I thinking? That's not because of reflexive. That's something I can actually take directly from the givens. Like, it's given that point P is equidistant from AB, so I can claim clearly that this is a given statement. Okay, for side 3, we'll go to the bottom. Again, if I just pick P to be a different place, instead of picking here, I'll pick it to be on AB. I can definitely claim that AP2 is congruent to B, P2. And again, the claim shall be backed up by the fact that it's a given statement. So now I have all these 3 statements, which I know to be true, coming together to prove the triangles that they're attached to are actually congruent. So triangle A, P2, P1, congruent to triangle B, P2, P1. And that's going to be because of the side-side-side triangle congruence theorem. Okay, so this is fantastic. I now know a lot more information about this diagram, but what I don't have yet, is a reason why it's perpendicular. The bisector is actually taken care of. The fact that is actually given to us, this right here, this piece, AP2 and BP2, does actually show that it's bisected. So like this statement directly says that this line is going to bisect the base. That's not the tough part. The tough part is actually going to be showing that it's perpendicular. I'm going to annotate the diagram a little bit differently. I'm going to call this angle 1 and this angle 2. And this is going to be for the purpose of actually helping me write this proof a little more clearly. So continue on to what I had before. Because these triangles are congruent, I can directly claim other relationships are also true. Now, there's a lot in here, but all I really care about is that angle 1 is congruent to angle 2. And that's because of CPC, TC. In other words, the definition of congruent triangles. Okay. It's the same thing. The CPC-TC is a common shortcut. I personally don't like it, but it's a common shortcut that's used to shortcut the definition of congruent triangles. Use whichever one you want. I notice a lot of people started adopting that phrasing. I think that's fantastic. Go ahead and do it. It's just not one that is a personal favorite of mine. Okay, so now angle 1 is congruent to angle 2. I still need to prove that they're actually going to be 90 degrees. So how do I do that? Well, I make a basic acknowledgement. If I want this to be 90 degrees, and again, the blue information here, I don't know yet. I'm trying to reach it. I have to make a basic observation that these two angles occur in a line. Well, if they occur in a line, they're supplementary because of the linear pair postulate. They have an equation because of their supplementaryism. And if I can know that they're congruent, then I can probably algebraically show that this will be 90 degrees. So continuing on a kind of a line of thought, if I know that angle 1 is congruent to angle 2, then I can certainly claim that the measurement of angle 1 is congruent to the measurement of angle 2. And if you're wondering why, well, that's just a definition of congruency. Okay. So we're going to use this in a moment, but I got to break away from our main proof and write kind of a secondary proof. So I'm going to kind of break this by using a dotted line. So we'll come back to it, but this is kind of like a new line of thought. Okay. So if I'm looking at angle 1 and angle 2, I can definitely claim that angle 1 and angle 2 are supplementary. And I can claim this because of the linear pair postulate. Well, if angle 1 and angle 2 are supplementary, then certainly the measurement of angle 1 plus the measurement of angle 2 equals 180 degrees. Okay. How I can claim that would be the definition of supplementary. It's amazing how much that one's come up this year. Hey, if I know measurement angle 1 plus measurement angle 2 equals 180 degrees, then I should be able to claim that the measurement of angle 1 plus the measurement of angle 1 equals 180 degrees. Now, you're probably saying, well, Mr. Collins, how in the world did you know that? Well, I actually have to bring in this piece. I know measurement of angle 1 and the measurement of angle 2 are the same, therefore I can do a substitution. I can substitute 2 for 1 and make this statement. The reason that's significant is now I can actually algebraically show what the value of measurement angle 1 has to be. And in this case, the measurement of angle 1 has to be equal to 90 degrees. How did I get that? Well, let's take a little sidebar. I'm not going to actually write this down, so I'm not writing the main proof, but I'll kind of show you algebraically how that worked out for us. Okay. And how that worked out is that if I have measurement of angle 1 plus a measurement of angle 1 equal 180, that's the same thing as saying 2 times the measurement of angle 1 equals 180, and that's the simplifying. And then if I divide both sides by 2, measure of angle 1 equals 90 degrees. And that's just kind of harkening back to like the individual algebraic steps that we use. But in the end, what we're doing here is simplifying and solving. And that's what I'm going to use for my justification. I did a little simplifying and solving in this step. Okay. Okay, so if measure of angle 1 is 90 degrees, if I combine some ideas here, I can certainly claim that the measurement of angle 1 equals 90 degrees, and the measurement of angle 2 equals 90 degrees. And the way I'm doing this, again, if you kind of trace the arrows, is because I'm just basically doing a substitution. I'm taking the measure 1 equals 90 and substituting it in for measurement angle 1 over here, making measurement angle 2 also equal to 90. Well, you guessed it, if measure 1 and 2 are both 90, that makes angle 1 and angle 2 right angles. And they're going to be right angles because of the definition of right angles. Okay. Well, if angle 1 and angle 2 are right, we were trying to prove this is a bisection, so we should, or I'm sorry, a perpendicular. So now that they're both right, we should be able to claim clearly that we have a perpendicular crossing. So I should be able to claim at this point that the line P1, P2 is perpendicular to AB. And if we're searching for reason, don't search too hard, because that's just a definition of perpendicular lines. Definition of perpendicular lines that meet a right angle. I've just shown the right angle. So here we have the proof that we were dealing with perpendicular lines, and above we had the proof that it was bisected. So these two pieces together would prove the original statement. Now this was lengthy. I'm not going to lie. But again, review the big steps. We had to prove that the triangles were congruent. That was step 1. Use triangle congruency to generate angle 1 and angle 2 having the same measure. Okay, so angle 1 and angle 2 having the same measurement. Show algebraically that they're both 90 degrees. And because they're both 90 degrees, boom, we have perpendicular lines. So both parts are necessary. I've circled them in purple. Here's where we showed that it bisects. Here's where we show it's perpendicular. I claim this proof is done. So let's move on to his converse. And the converse you're going to find is not going to be quite as harrowing. So the converse statement says that if a point P is perpendicular on a perpendicular bisector segment AB, then P is equidistant from both A and B. So let's do the right thing. Let's set up our pictures first. So I have point P in a segment AB. So here's our segment AB. And point P appears on the perpendicular bisector. That means we already have a perpendicular bisector. Like this one. Okay, so we have this perpendicular bisector. P appears somewhere on that bisector. Doesn't really matter where. In fact, I claim there's 2 placements. Again, I have a P1 here. I have a possible P2 here. So what I need to go about proving, which I'll place in blue. I'm sorry, this should be a perpendicular and a bisector. So what I need to kind of prove, which I'll write in blue, is that these are in fact equidistant. Equidistant, of course, mean the same measure, so that is amount to me proving these are congruent. These should also need to be proved, but that's going to be proved inherent just by the given, so I'm not going to try to write a separate case for that. So if I can prove these two blue lines are congruent, I'm in business. And while you're looking right away, I'm looking at another triangle. So it's going to be down to me proving that triangle AP2, P1 is congruent to B, P2, P1. In other words, these two triangles are congruent. Well, I already have this piece that was given to me. I have the fact that this is a right angle, which again, algebraically I can easily show is congruent to the one over here, because they're both right angles. It looks like I have a reflected piece in the middle. So really what this proof is about is showing these two triangles are going to be congruent, looking like I'm going to use SAS. And if they're congruent, so are my sides. So let's get to it. So step one, the big step, I have to prove triangle AP2, P1 is congruent to triangle B, P2, P1. You might be asking yourself, well, hey, Mr. Collins, isn't that we start at the last one? Yeah, triangle congruency is actually very, very useful for us, and it's going to give us a lot of information. I already kind of pre-stated that I'm going to use side angle side to do it. So let's get to her. So side 1, let's use a reflexive piece. So P2, P1 is going to be congruent to P2, P1, and that's going to be because of reflexive. The angle here in the middle is going to be a little bit more difficult to prove. I just can't claim they're congruent because all I know is that they're right. But I can show kind of using progressive algebra that these would have to be congruent. And again, this is a step a lot of people are skipping and you can't. I'm not doing this just for fun. I'm trying to demonstrate all the steps that are necessary in a real proof. So angle 1 and angle 2 are right. So let's get a relationship established. We know that because that is going to be given to us. If I know angle 1 and angle 2 are right, I definitely know the measure of angle 1 equals 90 and the measure of angle 2 equals 90. Okay. How can I conclude that? Well, that's the definition of what it means to be a right angle. Okay, so carrying this line of thought, if they're both equal to 90 degrees, then certainly measure of angle 1 is equal to the measure of angle 2 by using a little substitution. And if both measurements are the same, angle 1 is congruent to angle 2. And that's this definition of congruency. And again, please take note of all the individual steps needed to show that just because they're right angles, they actually are congruent. I know it seems kind of obvious, but again, you got to use all these steps to progressively show it, even though logically we could agree to that statement pretty instantaneously. Last step here. So when looking at the last side, it's going to be these AP2 and P2B, but that's just a given statement, so we just have to write it. So AP2 is congruent to P2B, and that's just given. Okay. Well, if we bring all three of these pieces together, we have this side length, we have these angles, and we have these side lengths. I can certainly claim that triangle AP2B, or P2P1, excuse me, is congruent to triangle BP2P1. And that's going to be because of the side angle side triangle congruence theorem. Now that these triangles have been kind of shown to be congruent, well, I was really only after these two sides, but I know for a fact that if these triangles are congruent, then all corresponding sides and angles are congruent. So that includes the two I wanted in the first place. So I can certainly claim then that AP2 is congruent to P2B, and that's going to be because of CPCTC. Corresponding parts of congruent triangles are congruent, which is also known as a definition of congruent triangles. Okay. So this is the part I was after, showing those two pieces are going to be congruent. So that's going to be that's the whole proof, and I know that seemed like a lot of work to prove something that seemed very logically simple, which is if I pick this point P to be on an equidistant from either endpoint of a segment, then that is going to be on the perpendicular bisector of that segment. And of course, going backwards, if it's on the perpendicular bisector of the segment, then it's going to be equidistant to the endpoints. But that is the perpendicular bisectors biconditional theorem. Guys, that's an incredibly convoluted proof. So again, if you have questions, please feel free to ask them. Please feel free to post them. And we can communicate and get you all the information you need about this proof that frankly we didn't get to talk about a lot in class. Okay, so thank you guys. Have a great day, a great night. Whenever you're watching this, pass the word, get other people to watch it too. Keep them caught up in class. Thank you.